Welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 4. This is lecture 4 and we are still continuing with the estimation of runoff, and today we will see another method called SCS-Curve number method for estimating runoff. Of course, SCS-Curve number method is used for estimating surface runoff volume. So, we will first talk about the estimation of surface runoff volume and then we will go into SCS-Curve number method in this lecture. Coming to estimation of surface runoff volume, we already know that volume is the total runoff occurring over a period of time, and in terms of discharge, if you want to present, it is nothing but the integral of discharge over a period of time, where Qt is the discharge at a time t and Vq is the volumetric runoff or runoff volume. And Qt, that is discharge, we have already had a discussion on several lectures on how to estimate or how to measure or determine discharge. So, we know how to determine discharge. That means, if we know the discharge, then over a period of time we can find out what is the total volume if we integrate over that particular time. So, based on our knowledge of hydrological cycle, which we have discussed in detail, we know that the estimation of runoff volume from a drainage basin or watershed or catchment, whatever term I said that we use these terms synonymously, it involves precipitation, infiltration, evaporation, transpiration, interception and depression storage. And just to recall, we discussed that when precipitation occurs, a part of that is of course intercepted by the plant canopies. Then of course, we have infiltration. When the water reaches the surface, infiltration takes place, and then once the infiltration capacity of the soil is satisfied, then of course the runoff starts, and during the process overland flow, the depression storage also takes place. And also we have abstractions called evaporation and transpiration, or combined together evapotranspiration, they also occur. So, that simply means that knowing the precipitation and considering the hydrological cycle, if we want to find out runoff volume, we need to have a fair idea of infiltration, evaporation, transpiration, interception and depression storage. That means all the possible abstractions actually. And we also have discussed almost all of them. So, we know that all these processes are complex and they can interact with the other to either enhance or reduce runoff. So, obviously, if evaporation is more, then evapotranspiration will be more. That means the total losses will be more. That means probably the runoff will be less, and so on. So, also these processes are temporally and especially distributed within a drainage basin. That means, over a drainage basin, all these processes, including precipitation or infiltration, they all vary over time and over space, because for example, we saw that precipitation is always differs over time and over space. Similarly, infiltration depends on the soil characteristics, and so if you take a large basin, then obviously there will be significant variation in the soil characteristics, and because of that infiltration will vary both over time and over space. So, all these processes, similarly evaporation or transpiration, interception, all these processes are temporally and especially distributed within the drainage basins. Thus, the manner in which these variables interact in time and space makes the direct determination of runoff very challenging. So, it is not really easy to, of course, we have seen different methods, but it is not really easy. And therefore, for estimating runoff from a drainage basin, we may use methods that reflect the combined effect of these variables in the basin. So, taking the combined effect of these variables on a drainage basin, we may estimate runoff, and SCS-Curve number method is one such method which takes into account the impact of all those characteristics affecting all these variables, the drainage basin characteristic impacting all these variables. So, this method, SCS-Curve number method or SCS-CN method, was developed by Soil Conservation Service in 1969, and already we have seen that now SCS is known as Natural Resource Conservation Service or NRCS. So, some latest textbooks or latest research papers, you might also find NRCS curve number method. So, it amounts the same because only the name has changed, SCS name has changed to NRCS. So, this method is either known as SCS curve number or NRCS curve number method. And the fundamental hypothesis of the SCS curve number are as follows. There are two fundamental hypotheses on which this curve number method is based. And the first one is that runoff starts after an initial abstraction IA has been satisfied. This abstraction consists principally of interception, surface storage and infiltration before the runoff begins. So, we have seen this picture while discussing the phi index also, or the average infiltration loss from the basin also. So, as you can see here, when precipitation starts, there is initial abstraction, and this initial abstraction consists of interception, that is which occurs before infiltration occurs, surface storage, that is there will be some storages, and infiltration, because we know that first soil infiltration capacity is satisfied, then only runoff starts. So, before runoff starts during a precipitation process, there will be some infiltration. So, this IA includes that part of infiltration. And then we are seeing here that this point onwards, when initial abstraction is satisfied, then we see that this the bar chart is divided into two parts, one representing this F, which is infiltration after the runoff has started, and VQ, that is the runoff actually. So, that is once this initial abstraction is satisfied, then when runoff process starts, then of course there will be infiltration continuing. So, infiltration will be before the runoff started and after the commencement of runoff. Both times infiltration will continue, and that we know that as the soil comes in contact with the soil surface, the precipitation comes in the contact of soil surface, then infiltration process begins. So, this is what basically it reflects. So, this graph shows the relationship between P, VQ, IA and F. So, the P is the precipitation, VQ is the runoff volume, IA is initial abstraction and F is the infiltration. So, this is the first fundamental hypothesis, that runoff starts after an initial abstraction has been satisfied, and this consists of interception, surface storage and infiltration before the runoff began. Then second hypothesis says that the ratio of actual retention of rainfall to potential maximum retention is equal to the ratio of direct runoff to the rainfall minus initial abstraction. So, mathematically this can be expressed like this, that if you take the left hand side, what it is saying, that P minus IA minus VQ. So, P minus IA minus VQ is nothing but F here, that is the actual infiltration which has gone into the soil, and this S represents here the maximum potential retention of water by the drainage basin. That means whatever total has been absorbed by the basin. So, the actual retention, that is actual infiltration, and the maximum potential retention, the ratio is represented on the left side, and that is equal to potential, that is equal to ratio of direct runoff, that is VQ, which we are seeing here, divided by rainfall minus initial abstraction. So, rainfall minus initial abstraction, that is of course rainfall minus initial abstraction will represent this VQ and F, and VQ divided by this will be same as on the left hand side. So, here VQ is the runoff volume uniformly distributed over the drainage basin, P is the main precipitation over the drainage basin, S already we have seen is maximum potential retention of water by drainage basin. So, this is the second hypothesis, one on which SCS curve number method has is based. Now, if we talk about equation number 2, that like we saw this equation here, this we can manipulate this equation and write in this form, that is VQ equals to P minus A square divided by P minus A plus S, and this is equation number 3 we are calling. So, simply we have just manipulated that particular equation to represent in this form. Now, the quantity IA, which is the initial abstraction, can be expressed as a function of S. So, this is another assumption that this entire IA can be represented in terms of maximum potential retention S of the drainage basin. And age per soil conservation service, this IA is equal to 0.2S, which simply means, physically means that for a given storm, 20% of potential maximum retention is the initial abstraction before runoff begins. So, 20% of potential maximum retention is the initial abstraction. So, IA equals to 0.2S. So, that simply means we can replace that following the SCS curve number assumption, and if we consider that IA equals to 0.2S, then equation 3, if you put IA equals to 0.2S here and IA equals to 0.2S here, then its equation reduces to this form: VQ equals to P minus 0.2S square divided by P plus 0.8S. This is equation number 4, and this is the SCS curve number equation, the basic equation of the SCS curve number method, provided we go by this assumption that IA is equal to 0.2S. Otherwise, we can always follow equation number 3, that these two are the same equations, only in this equation number 3, IA equal to 0.2S, which was suggested by SCS curve number, has been replaced. So, if you look into this, evidently this is a one parameter model containing S as a parameter. So, if you know S parameter S for a drainage basin, and if you know the precipitation, using this method you can determine the runoff volume VQ. So, it's a simple method from that sense, because it's a parameter, it has only a single parameter model. However, different researchers have recommended varying value of IA. For example, Hawkins and others in 2002, they recommended a value of IA equals to 0.5% of S. So, I mean this, though SCS recommended IA equals to 0.2S, but this has been a matter of contention by among the researchers, and Hawkins and his team, they collected data from a large number of watersheds, and they analyzed and published a paper where they showed that IA is just 5% of S compared to 20% of S, which was assumed by SCS way back when this method was devised. Similarly, for Indian conditions also, different researchers have come up, like people have used 0.1 to 0.3S value. Typically, IA equals to 0.3S, but this is always a matter of contention. That is why many times we use S, or will follow that curve number as a calibration parameter in any model where we use this SCS curve number method. Now, coming to estimation of maximum potential retention, that is S, which is evidently the only parameter of this model. This estimation of watershed potential maximum retention H, which depends on SVL complex, that is soil, vegetation and land use complex in the watershed, is challenging. That is, it's not straightforward, it's pretty difficult task, and that is why SCS developed the concept of dimensionless curve number CN, and that is why the name of the method SCS curve number. And basically this curve number is related to S, and it helps us determine the value of this parameter, maximum potential retention. And this relationship between CN and S is given by this relationship, this equation number 5, that is S equal to 25,400 by CN minus 254, where S is in millimeters. So, if we relate S and CN, so we know that SCS curve number method had only one parameter S, and because now S is being expressed in terms of S, so that simply means the CN is the only parameter that needs to be determined in order to be able to apply SCS curve number method and determine the volume of runoff. So, that is a simple method. Now, this curve number is a relative measure of retention of water by a given SVL complex, that is soil, vegetation, land use complex, and takes on values from 0 to 100. So, curve number value could vary from 0 to 100 theoretically, and when curve number is 100, then obviously if you put 100 here, S becomes 0, and that simply means what? If S is 0, then VQ, entire VQ will become P. That means the entire precipitation will be converted into runoff, and that could happen only say it is a paved area or completely saturated area, where so if it is a paved area, completely saturated area, then we can say that curve number of such a such an entity will be 100, because there the entire runoff rain precipitation will get converted into runoff. On the other extreme, Cn, when Cn is 0, then S is infinity and VQ is 0, meaning the entire precipitation infiltrates and there is no runoff, which could have the vegetative humid areas which we have earlier seen some of cases. But typically, though theoretically the value ranges between 0 and 100, but typically the lower limit is around 30 to 40, somewhere 30 to 40, and as earlier mentioned that typically whenever a model uses SCS curve number method, curve number is always taken as a calibration parameter that we calibrate, and we try to find out the exact value or relatively better value of curve number that suits a particular drainage basin for a given data set. And for determining the curve number, SCS classified around 8,500 soil series into 4 hydrological soil groups according to their infiltration characteristics, and the hydrologic soil groups are designated as A, B, C, D, and this is how this table looks like. That hydrological soil group is given A, B, C, D, and of course it is related to the infiltration rate of the soil. So you can see that hydrologic soil group has a very high infiltration, 7.62 to 11.43 millimeter per hour. So high infiltration rates, deep, well drained sands and gravels, that they fall under hydrological soil group A. Soil group B has infiltration between 3.81 to 7.62 millimeter per hour. So it has moderate infiltration rate, moderately deep, moderately well drained soils with moderately coarse textures. C, hydrologic soil group C, the rate is 1.27 to 3.81 millimeter per hour. It is slow infiltration rates, soils with layers or soils with moderately fine textures, and category D having the lowest infiltration rate, that is up to 1.27 millimeter per hour, that is very slow infiltration rates, clay soils, high water table or shallow impervious layer. So these are the conditions and these are the infiltration rates. So if you know the infiltration rate of the soil in your basin, you know which hydrological soil group you are dealing with. So that's the first step. And then obviously in SCS curve number method, the antecedent moisture content AMC condition, the AMC antecedent moisture content condition represents the state of the soil moisture in a particular area or catchment at the beginning of the rainfall runoff event, and it is basically classified into three groups: AMC 1, 2 and 3. And of course, it is based on the total rain that was recorded in the previous 5 years. That means any rainfall runoff event starts today, then what was the rainfall in previous 5 days, that is taken into consideration. And of course, there are 2 seasons that are identified. So dormant season and growing season. Dormant season, that means there is no crop, and growing season, that means crops are being cultivated. So if dormant season, if previous 5-day rainfall is less than 13 mm, then we are AMC 1. If it is between 13 and 22 mm, then we are MC 2, and if it is greater than 28 mm, then we are MC 3. Similarly, in the growing season, the values range from 36 millimeters for AMC 1, 36 to 53 millimeters for AMC 2, and greater than 53 millimeters for AMC 3. And of course, dry condition, AMC 1 represents dry condition, dry or relatively dry antecedent moisture content. That is, the soil has low moisture content and it can absorb significant rainfall before generating runoff. AMC 2 represents average condition, represents average or intermediate antecedent moisture condition, that the soil is neither very dry nor wet, whereas AMC3 the extreme, that wet condition, it corresponds to wet or saturated antecedent moisture condition, that is the soil has a high moisture content and it cannot absorb additional rainfall. So, obviously, you have to know the soil, you have to know the antecedent moisture condition in order to obtain the values of curve number. So, coming to curve number determination, knowing the hydrological soil group, as we have seen A, B, C, D, and the curve number can be obtained from the standard tables provided by NRCS or SCS basically. And this table is curve number for AMC2 other than urban area. So, this is not for urban area, other than urban area. This that means for forest, cultivated land. As you can see here, land uses are cultivated, orchards, forest, pasture, wasteland, hard surfaces, all are there other than urban areas. So, here you can see that under each category there are some treatments, cultivation treatments, and the hydrological condition also is being considered, and then for different soil groups A, B, C, D, the curve number is listed here. So, for example, if you are in cultivated area and it is contoured and terraced land, and it is having hydrological condition is good, and we are in soil group A, then the value will be 62, if group B then 71, group C then 77, and group D then 81. So, values range from 62 to 81. Similarly, if we are in forest, which is a dense forest, then obviously the value will be 26 to 61. So, 26 for soil group A, that is very high infiltration, that means runoff potential will be low, and D, the infiltration is low. So, the runoff potential will be very, very high, and these tables have been taken from Soil Conservation Service 1986, Urban Hydrology for a Small Watershed, Technical Release 55, USDA report number TR 55, that is USDA, and that, as I said, that because all these values come, the curve number values which we always refer from the SCA reports. So, that is why we always calibrate this. This is used as a calibration parameter in any of the models, just to find out the relevant value of curve number for the watershed. Suppose any modeling area we are doing in for any Indian watershed, then we obtain the basic value from the SCS table, but we always calibrate that for Indian conditions, so that we get a reasonable good value for our case. And this table is for urban areas. So, similar table here, the land use description will change, that is high density residential, industrial, low density residential, open spaces, parking and paved spaces. So, obviously parking and paved spaces 100% pervious area. So, you will find that almost the curve number is 98. That means most of it, as we said, that 100 means 100% precipitation gets converted into runoff. But here the value is almost 98. So, that means 98% of your precipitation will get converted into runoff. That is what it means. But industrial, similarly, it will be, values will change from residential to parking or paved areas. So, this is for urban areas. Now, once we know the curve number, that is from knowing the hydrological soil group, under what conditions we are, what hydrological conditions we have, what kind of cultivation practices or what kind of paved area we have in the area, we will know the curve number from previous two tables just now we saw. And those values are given for average condition, that is for AMC2 condition. So, value which you obtain from previous two tables is for AMC2 condition. But as we already saw that depending upon the previous 5-day rainfall, the AMC could be 1, 2 and 3, it could be dry, it could be wet, it could be average. So, accordingly, once we know AMC curve number for AMC2, then obviously if we are dealing with a situation of AMC1 or AMC3, then we have to get the corresponding value. So, if we get 90 and we have AMC1, then the value that we will use in model is 78. Similarly, if it is AMC3, then we will use a value of 96. So, that means knowing the soil group and land use practices, we will get the curve number from standard tables for AMC2, and then knowing AMC antecedent moisture content or moisture condition, we will decide which AMC group we belong to, and then accordingly we will convert get the correct value of curve number. That is how it works. Now, another important thing is that besides this table just now we saw, there are some equations also available for determining the curve number for AMC and AMC1 or AMC3 if provided we have AMC2 values. So, these relationship, as you can see, they are in terms of AMC2. So, knowing AMC-CN curve number value for AMC2, we can also mathematically determine the values of curve number for AMC1 and AMC2. And already as we saw in runoff coefficient case, the watershed may not have a homogeneous land use or homogeneous characteristics. So, we may use different curve numbers for different land cover or soil types. So, that means as we saw yesterday that there could be 3 different uses, and that means there are 3 different curve number values you will get. So, we have to know the area represented by a particular curve number in order to get the weighted curve number that will be applicable in our case. So, this is how we obtain this curve number, weighted curve number we can obtain here. So, using this relationship we can do that. So, that simply means that the steps are very clear, which will be still when we take up the problems we can be very clear. And in earlier times when computational facilities were not good, and then graphical solution was also developed, where this is cumulative direct runoff, cumulative rainfall, and for different curve numbers you have relationships. So, if you know the rainfall and if you know the applicable curve number, you can read this value from here, and this assumes IA equals to 0.2s, that is the original SCS curve number procedure. Let us take an example. A 71 square kilometer urban watershed includes 60 square kilometers of open area with 80% grass cover and 11 square kilometers of industrial development, that is 72% impervious. The soil is in SCS group B. Estimate VQ and total runoff volume for a 24-hour rainfall with P equals to 45 mm for MC3 condition. So, of course, we have to find out the area weighted average curve number for MC2, that is the baseline condition, and for that we can refer this table here. We have open area with 80% grass. So, open area more than 80% grass we are in group 2. So, obviously, the curve number is 61, and it is given that this area is 60 square kilometers. So, for 60 square kilometers in the basin we have curve number value of 61. Similarly, we have industrial development, that is 22 pervious. So, industrial 22 pervious, the value is 88, and that is for 11, area is 11 square kilometers. So, we know 2 uses, 2 curve numbers, 2 areas. So, of course, we can find out the weighted curve number using this relationship, and that comes out to be 65.18. So, 65.18 is AMC2 condition area, but we know that we are dealing with AMC3. So, that means we have to use either the conversion table or this relationship which relates the curve number for AMC3 to curve number for AMC2. So, by putting the curve number for AMC2 condition here, we can get the curve number AMC3 condition 81.15. And then of course, S value can be calculated using this standard relationship because we know the curve number. So, the value comes out to be 59 millimeters. And of course, this IA equal to 0.2s is 11.8 mm. Since our S value is greater than is 0.2s, that is initial abstraction, that means there will be runoff, that is less than rainfall value of 45 mm. So, there will be runoff generated. So, then we can use this relationship and put the values of P 45 mm which is known, and the S which is known to us, and then we get the value of VQ equals to 11.59. But we have to also get the in volumetric terms. So, obviously, the 11.595 millimeters we have to multiply with the total area also, Of course, this is a unit conversion just to get everything in meters, and so we get this value of 8,48,450 cubic meters, or we can say that it is 0.85 million cubic meters. So the runoff for that runoff volume for the given data set was 0.85 million cubic meter. We will quickly take another example. The curve number of a watershed of 40 hectares area under given hydrological soil group, land use and management practices, and anticipated moisture condition 2 is 80. The initial abstraction is 20% of maximum retention. For the rainfall event of 40 mm, find the direct runoff in millimeters, and this question has been taken from GATE 2020. So already we have been given curve number. So maximum potential retention we can obtain using this relationship, which comes out to be 63.5 mm. And we have also be given IA equals to 0.2s, that is initial abstraction 20% of maximum retention. So that means we can use this simplified formula where already IA is taken is 0.2s. So putting the value of P and S, already we know P equals to P value is given here 40 mm, and S value already we have calculated 63.5 mm. Putting these values, we can find out VQ, which comes out to be 8.21 mm. So that this is what in this lecture we saw SCS-Curve number method, which basically uses SVL, soil, vegetation and land use complex of a given basin. And of course, we have to use the standard tables and get the curve number from there, and then use the procedure we have discussed. So this is one way of finding out the direct runoff volume from a given basin. Thank you very much. Please give your feedback and also raise your doubts or questions so that it can be answered on the forum. Thank you.